All right, everyone. Apologies for the delay. It was entirely my fault. We're absolutely delighted to have a very old friend, David E. Kaplan, visiting for the day. He'll tell us about the wonderfully strange world of nonlinear modifications of quantum mechanics that are not as dead as they were when Joel Poshinsky killed them. We'll be going to dinner with David. Anyone who wants to come, we'll gather in the lobby at around 6:30 and maybe send an email ahead of time so I have some idea of who wants to come. You want this pointer?
I'll use this. Okay. Hey, thanks for having me. I'm going to talk about nonlinear quantum mechanics, both this work I did with Surjit Rajendran during COVID. It was very COVID-induced theoretical exploration, but we have experimental colleagues who have also dived in. And what we'll see today is that Joe didn't actually kill it. He explained what you're supposed to do to make it causal, because Weinberg screwed it up. And but he also discovered D-branes that year, and that became very hot. So he kind of but I'll also describe another reason why he quickly shifted away from it too. This is sort of the ice-breaking slide. If somebody is modifying quantum mechanics, they're either close to retirement or crazy. I hope I have many years left in my future, so you can guess where I live. I show this photograph only because to remind you how arcane the rules of quantum mechanics are, and even when quantum mechanics taught, how misled even some people teaching it are when they talk about things like measurement, etc. But I'd like to talk generally about how rigid are the rules of quantum mechanics, what sort of modifications can be made. And what I'll show you is that what we found after a long bit of work, that it's surprisingly easy to do it in a healthy way. And therefore, we think it's interesting. The natural thing people think about when modifying quantum mechanics, or as sort of as an emotional response to quantum mechanics, is getting rid of probability. And the problem with trying to get rid of probability are all of the old hidden variable constraints, Bell's inequality, etc. But there's also just really at the core, when you first teach quantum mechanics, if you start with Stern-Gerlach, you talk about properties like rotational invariance and measurements with a continuous choice of angle when you measure a spin, and outcomes which are discrete. And so the question is, when you're parameterizing a system, for example, the ground state of hydrogen or hydrogen below a certain energy level, you really have a discrete set of observables. And if you want to describe the state with continuous variables, say the position of the electron or something, you get into trouble. You need to do something with that continuous information. You don't want an infinity, for example, of degenerate ground states. So probability for a long time has been desired to be messed with. And it's in some ways associated with the collapse of the wave function, which also people want to mess with, and we'll get to that too. But a much simpler thing to mess with is linearity. The linearity, what I mean is that the Schrodinger equation is linear in the state. And the question is, could you mess with the linearity that the time evolution is driven by a function maybe that depends on the state itself? If you do that, then it really cares about, for example, the wave function. And so we can ask how severe the constraints would be on messing with the Schrodinger equation, and namely the state dependence of things like the Hamiltonian. And this is, in terms of Weinberg, this was sort of the direction that he was thinking in. In general, I'd say linearity violations of quantum mechanics have been explored since de Broglie wrote some hundreds of pages of treatise on. He suggested quantum mechanics is a linear approximation of a more complete theory, again, linear in terms of the wave function, and then wrote hundreds of pages of numerical calculations of Schrodinger equation plus higher order terms. Kibble actually wrote down something which is closest to what I'll present here, which is he took scalar field theory and added expectation values of fields to the action, and then, or to the Hamiltonian, and then to the path integral, and then explore the consequences of that. He only did it for very trivial theories, but in a sense, this was the thing that will take care of things like locality and causality. In fact, that was motivated by a broader set of just words, which is, what if everything in the world is quantum except gravity, and gravity is classical? You never have to worry about a quantum theory of gravity. And so the sort of most straightforward way to describe that is to write down a classical equation where the Einstein tensor is the expectation value of T mu nu. And what you can see without too much work is that this predicts nonlinearity in quantum mechanics. And so in fact, Page enlisted Gailkert to do experiments where they had some quantum measuring device, and then they had a big mass that they moved back and forth. And then the Cavendish experiment to look at that mass was supposed to look at the other part of the wave function where that mass would have been based on a quantum measurement. And I will describe in this talk those types of experiments. They were able to constrain that to something like order 1. The strength of gravity. And it's not clear how good the fidelity of their quantum device was. So I don't actually know if it ends up putting a constraint, but that was sort of the classic experiment you'd go after. Weinberg just formally extended non-relativistic quantum mechanics, and he wanted to do it as general as possible, not in the position basis, and not surprisingly ran into locality violations, which Joe pointed out. Gibson also pointed this out. What Joe wrote in his paper was the requirements on such a time evolution operator, which could depend on the state, but what you'd have to do to remain a causal theory. He also pointed out something we'll point out here too, which is that nonlinear quantum mechanics actually is generally locally an attractor towards linear quantum mechanics. And this is a quantum dilution that happens naturally. All right. So I'll talk about the framework in quantum field theory. I'll talk about the single particle quantum mechanics version, which would be the limit. It would look something like maybe what Weinberg wrote down. And then we'll talk a little bit about causality and a lot more about measurement. And then we'll talk about constraints and experiments. And then we'll talk about this dilution effect and how we're incredibly sensitive to the history of cosmology and quantum amplification. And then we'll talk about things that you could still measure in that context. All right. Think of quantum field theory in the Schrodinger picture and in the canonical language, in the sense that there's still a Schrodinger equation, but the Hamiltonian is built out of fields. And so it'll be some local Hamiltonian that we write down, made of fields, in this case, just in terms of space. And the time evolution operator in this language is just e to the minus iht. You might say, well, this is already nonlinear. I'm writing nonlinear terms in the Hamiltonian density. What do I mean? And what I mean by nonlinear is that we're going to add terms that depend on the quantum state itself, which we often ignore when we do field theory. We write a path integral. We just write down vacuum correlators, things like that. Now we actually care about the state. So for example, one thing you could do is for Hamiltonian, you could write down an extra term. And the extra term itself maybe have expectation values of operators. Operators that live in the theory, and that if they are Hermitian, so here's an example where O1 and O2 could be Hermitian operators. The combination of the two satisfies all the symmetries you want to preserve in the Hamiltonian, but now one has an expectation value around it. And you can show pretty trivially that if both of these are Hermitian, then the time derivative of the norm is 0, so that you can still have a probabilistic interpretation of measurement. You can build this Hamiltonian or these extra terms in such a way to conserve things like energy, but also just other symmetries you might care about by noticing the following, perhaps silly thing, which is that I can derive the Schrodinger equation from a, let's call it an auxiliary action like this, where this is chi dot is time derivative with respect to, or derivative with respect to time. These are inner products of the state. And here is the matrix element of the Hamiltonian. I can derive this Schrodinger equation by saying that the path that the state takes minimizes this action. So if you vary with respect to the paths that the state takes in time, you will get back to Schrodinger equation. And so if I do that, I can also add terms that are at higher order in the state. So this term is second order in the state. I can add terms which are fourth order in the state vector. And these are again operators in the theory. And when I vary, then I get the Schrodinger equation plus two terms, these sort of symmetrized terms. And the nice thing about this is if I have an auxiliary action, I can use things like Noether's theorem and describe energy conservation in other conserved quantities. So this is just a way to generate a term like this. And it also gives you a sense of the sort of expansion that we're doing here. Like higher order terms are higher order in the number of state vectors that you put in. So you can think of this as a general expansion in chi's. If you want to describe this in the path integral, and I'm being a Hamiltonian guy, which is to say that the path integral is just a solution to the Schrodinger equation. If I want to generate a path integral, I can do it perturbatively. I can compute those expectation values at, let's say, zero order in epsilon, where epsilon is, say, a small parameter for these additional terms, calculate that at zeroth order, put those in, and then those terms simply become background fields in the path integral. So I have some phi field, full quantum phi field. I can calculate correlations, but I'm doing it with an action which includes these background expectation values that I computed in the zeroth order theory. So there's nothing complicated or new here in the sense of I know how to calculate path integrals even in the presence of a source term. And so that's all this is.
So but you don't integrate over all the states side.
No, the states that appear in here really are the state in that sense. And so what I do in the Hamiltonian language is I calculate the expectation value. So I imagine the time evolution where epsilon is equal to 0. So I start for some initial state, I do the time evolution, and I calculated now some space-time function at that point. And now I take that space-time function and I can derive the path integral where these things just are space-time functions that live in the Hamiltonian. And so in that case, this is still an integration over all paths of phi, but this has been determined at least to zeroth order in the theory.
Oh, yeah, because in the previous slide, you said the principal usually to minimize the by scan over all the
this
side, right?
Yeah, this I use as a sort of a trick to generate not only just the Schrodinger equation, but the Schrodinger equation plus these extra terms. It's not necessary to do it. You can think even crazier thoughts that what if I do a path integral over this action? Maybe the Schrodinger equation itself is not, maybe that's a classical path. There's a meta quantum theory.
Oh,
So, but I'm sorry I brought all that up. I just thought it was cute. But really, this is just a language to think about how to add additional state dependent terms and what it means to add higher order terms. Yeah. But here, just think about it as a background field. We calculate the expectation value at epsilon equals 0, and then we plug in background fields. Those background fields do depend on that initial state in the time evolution in the linear theory. And then when I put them back in, they source something else.
This, just to leave in order in epsilon, this would be an approximation to ordinary quantum mechanics.
Yeah, I mean,
for this field.
in a sense, to see nonlinear effects, you need to do something which sort of splits the wave function, and then you need to detect it. So it's sort of a second order effect. First is a quantum effect, and the second is the nonlinear.
So higher orders are, what? So this is an integral over space-time. How are we supposed to think about O1 of t? Normally we think of expectation value as a function of time, where you go with some Hamiltonian.
Right.
Now will be this nonlinear Hamiltonian, which
Yeah, first at epsilon equals 0, I have to calculate the full time evolution of this background. So I calculate the full time evolution. Now I have a space-time function. So in the Schrodinger picture, the state is time dependent, the operator is space dependent.
Okay, so
And then I just insert it. So this operator is some function of the fields themselves. But here in the path integral, they just play the role of the background. I'm not varying with respect to anything in here.
I'm confused by something, because so leading order in epsilon is just like a vev for the O's, right? So they're
Not an ev in expectation value. It's not a vector,
Sorry.
but yes, it depends on the initial state.
So I'm not doing the path integral with the usual, I'm not doing the usual path integral. I'm not doing the usual path integral with boundary condition for everything vanishes.
So our normal method is we go to Euclidean space, we do vacuum because we put in a little epsilon credit.
Yeah.
So that's not that
You're not
epsilon.
doing that, okay.
Not doing that,
Okay.
because what I want to discover is the state dependence. So I really care about the initial state, this path integral, the initial state.
So there really is some initial and final states of this path integral.
Yes.
So you're not doing the usual.
Yes, or I have an initial state and maybe this is a function of the final state, yeah.
Okay. Otherwise, if we didn't do that, it would be completely absorbed into what we mean by the depth, right?
Yeah, I would argue that there's a problem in deriving that path integral in the language so we have nonlinear quantum mechanics. I'm talking about an initial state, a non-trivial initial state, not the vacuum state. And I'm going to ask how that state time evolves. So we don't do that because what we typically want to do is say I can create any state out of the vacuum and I can calculate correlators and things like that. But now I want, big, complicated, coherent states even that I can build. And that state now lives in the action itself.
But we normally say that we can get all that physics by talking about vacuum correlators, just inserting a lot of operators. And
yes,
so it's like we
right
did that in this context.
So at all orders, what is this? This is a nested set of path integrals. Path integrals that depend on those initial states. So depending on the properties of the O's and their commutations with the Hamiltonian, there are simple, almost trivial versions of this. But for the operators we care about, which will not commute with the Hamiltonian, I can put it in the interaction basis and try to derive a closed form path integral and have not succeeded. That's so simplest example, say, was a Yukawa coupling. I like this for many reasons, but mainly if I take a Yukawa coupling and I add a couple of extra terms, which look like expectation values, a part of that operator, this is associated with a long-range force. This is something that was not played around with by Weinberg or Polchinski. And then what you can ask for, just like we do in electromagnetism, we can ask what the single particle quantum mechanics, Hamiltonian and time evolution should look like in this theory. So I want to go to a theory. I'm not using the photon now, I'm using just a scalar, but it's the same idea. I'm going to focus just on this term, which is the expectation value of phi. And I'm asking the non-relativistic theory, where I just turn these into, say, wave functions, what is the computation of the expectation value of phi? And of course, phi itself, that state may have waves associated with it. There may be some interesting initial condition for phi, but phi also is, of course, sourced by psi bar psi in the original term. And so if you then ask what the expectation value of phi is in the single particle limit, it really is just a wave function squared times the retarded Green's function, which then sources is like a charge density sourcing phi at some later time x. So in other words, the single particle quantum mechanical analog will look just like this. This is sort of a term that Weinberg would have written down, but we just add a crappy Green's function there to make it relativistic or causal. So that what the interaction is between the wave function and itself, but in its past light cone. And then when you go to multiple particles, you can extend this to multiple Green's functions, but it always gets something which looks in a simple way causal. We can do this in QED and even in gravity. In QED, you might put an expectation value, say, around the photon itself. You have to be a little bit careful about gauge invariance in the Hamiltonian. When you write a Hamiltonian, often you'll choose a gauge. And so maybe you could choose the Weil gauge, for example, and choose an expectation value to live there. Or if you don't want to deal with that or don't want to think about that for the rest of the talk, you can think about putting an expectation value around F mu, and this looks like then just a source term for a photon. Similarly, and I will not talk about that much here, you can do the same thing by adding an expectation value around the graviton, or not the graviton, but the gravitational metric as an operator. Again, if you do the Hamiltonian version of this, you have to fix a gauge, you have to decide what you mean, and that is an entirely other talk, and I will not dive into that, but I'm happy to talk about that. All right. This is the part of the talk, depending on how you grew up, it makes you very upset, or it's obvious and you fall asleep. So let's see what happens. It's almost like a psychological test. Measurement in quantum mechanics. How does measurement work? Well, we know how time evolution works. Time evolution happens with the unitary operator, and measurement then is just the fact that the Hamiltonian contains a term which is an interaction term between something you want to measure and your measuring device. And when you bring those two close to each other in whatever proverbial way you need to, time evolution then, for example, a spin pointing in some random direction is a linear combination of spin up and spin down along the direction that, say, your device, say, Stern-Gerlach measures, plus the other bells and whistles that allow the human to look at what the device did, and that's measurement. Of course, the state is this linear combination of these two. You evolve an initial state of both into an entangled final state, the both, the various spins and the various states of the detector, which we will pick to be stationary states. And we'd like that, then we come in a day later, we can look at our device and still see that that was the measurement. And then what do? We, of course, we trace over all the crappy details of your detector because you don't really know what the quantum state was. And we end up with a probabilistic interpretation, which is that you have a probability of measuring the various values of I, depending on how the initial state was built, the alphas and the betas. In nonlinear quantum mechanics, where we've added some state-dependent term to the Hamiltonian, stationary states are not generally orthogonal. You have state one, which is a stationary state, but it's a nonlinear term, that Schrodinger equation. And state two could be a stationary state as well, but state 1 + 2 may not be a stationary state. And so it actually depends on what the initial conditions of the experiment are. And if you don't know, say, for example, the initial conditions of chi, or you haven't set up your experiment in a good way, so you don't know what the outcome is, you don't know what alpha and beta are, there's no guarantee that you're going to choose a detector such that the stationary states of the detector are orthogonal to each other.
I'm sorry, David, I thought that the usual point is that overlap, regardless, is super exponentially small.
Yes, and what we'll see,
Even if you don't ask for it to be zero, it just is super
it's
exponentially
extremely small. It's typically extremely small. But what we're going to do is we're going to create macroscopic superpositions. And those macroscopic superpositions appearing in the Hamiltonian will then macroscopically affect both states. So there'll be a term which is an expectation value of something, which is a linear combination of two macroscopically different things. And that on the whole can affect then both outcomes. They'll each have overlap with the two effectively. I'll give an explicit example. This is simply to say that with nonlinearity, you will get some epsilonic change to the outcome of the measurement. For example, everything I'm about to say now is what's true in linear quantum mechanics. I can set up a system where I have, for example, a spin 1/2 particle, which is prepared spin up in the x direction. I can have an experimentalist or a non-sentient being with no consciousness, a robot or something like that, so we don't have to talk about consciousness. and then a pair of photodetectors with a laser, which could be pointed in either direction. And the initial state, this describes in a sense the initial state. It represents the full quantum state of the system, which includes the spin, the experimentalist robot, the photodetectors, the laser, and the environment in the lab. And the goal is to create a macroscopic superposition state. And to do that, we will do a tiny quantum measurement, and we will macroscopically do different outcomes based on that measurement. So in linear quantum mechanics, what happens if I measured this particle in the z direction? One outcome is spin up. If I get spin up, the robot will turn the laser on, pointing to the detector on the left. And if I measure spin down, they will turn the laser to the right, and the photodetectors will light up. And the state, the full quantum state of the system, of course, is 1/√2 plus z, a laser pointing to the left, and the environment affected by a laser pointing to the left, plus minus z, laser pointing to the right, the full environment affected by a laser pointing to the right. That is the quantum state of the theory. I could be, for example, in part of that quantum state, and I'll say, oh, look, it's pointing up, because let's turn on the laser. There's a laser, I see what's going on. And then there's a version of me saying the same thing about the laser to the right. So in linear quantum mechanics, these are the two parts of the wave function. And you can look at transition matrix elements. If I want to ask questions, I being someone that states, oh, I saw spin up and the laser is pointing to the left, I can ask about, say, that operator, that term in the Hamiltonian, and I can ask, is it non-zero over here? Is this detector going to light up? And the answer is yes. And then I can ask, is this detector over here going to light up? And the answer is no, because there's no support in this part of the wave function for an electromagnetic wave on this part of the room. It's because that expectation value of the laser pointing to the left is 0 on the right side. Now I'm going to turn on nonlinear quantum mechanics. And nonlinear quantum mechanics has an additional term which depends just on the full expectation value of the photon field. Now I can ask about the transition matrix element that involved that term, and that term has an expectation value already living in there, which I can compute, and is just some number or function of space-time. And now what's true is that that full function of space-time has support both on the left and the right. And so this matrix element, does this detector light up? Does this detector light up? The answer is yes, even for this observer on the left. And that's because the expectation value of the photon field is non-zero for the total state. And so what you're seeing is something Polchinski called the Everett phone. This is communications between the worlds. All right. Now, I'm adding this nonlinear term to quantum mechanics, but we have these very precise quantum experiments, AMO, blah, blah, blah. We should know quantum mechanics exceedingly well. We use quantum mechanics to measure other things incredibly accurately. So shouldn't we see that this is already deeply constrained? Let's look at that, for example, photon coupling. The concern would be that for example, the Lamb shift, the two S and 2p states are almost exactly the same energy in the hydrogen atom, but their wave functions are order 1 different from each other. And if there really was a term that depended on the wave function squared interacting with the wave function, that should contribute to energy splitting. The problem is, in linear quantum mechanics, you can separate the center of mass variable from the just overall position, say the position of the proton. Whereas if you add a nonlinear term, you cannot do that. That in fact, what matters is the full wave function of the atom. And so the way we do these Lamb shift experiments is, say we trap the atom, or really they're in a semi-dilute gas, and we look for these energy levels. And the wave function of the electron is spread over almost a micron. In fact, the wave function of the proton is also spread over almost that same micron with tiny angstrom-like differences. So the full charge density that goes into there is incredibly small. So in fact, the fact that the atom, which in linear quantum mechanics, it doesn't matter if proton is pinned to its point, or is the size of Andromeda Galaxy, the energy levels of that hydrogen are exactly the same. Here, we care about how spread out the wave function of the electron and proton are. And for classic measurements, that extra dilution actually only puts a bound of roughly 10 to the minus 2 if we're being generous to those experiments. And so what you really have to focus on, and this, because it wasn't in Weinberg's original paper, and therefore was missed by the experimental efforts that followed him, you know, 27 different measurements to put constraints on his version of epsilon. All of those experiments are essentially irrelevant to putting tight constraints on this. What you want to do is to, first of all, if you can, there are two options. One is trap things to an incredibly tiny region, the best you can. Leave it charged. So if you trap an ion, for example, then you have that charge density that will affect the energy levels of the ion. And then what you can do is say, take the ion and put it in some quantum superposition of energy eigenstates. You split the ion, it's an interferometer, and then you bring the ion back together. This is 0 and 1 states. And that phase difference between the two in linear quantum mechanics depends on the energy. But now the phase difference in nonlinear quantum mechanics also depends on the relative weight of the two parts of the wave function. So you're actually, in a sense, measuring the Born parameters associated with probability in the measurement. And so we use that, or we pose experiments like this that allows you to test and for different intensities of P n squared 1 minus P squared, these are the amplitudes, for different values of P, look for different phases. And that helps us combat systematics. Of course, Surjit and I didn't do this. Professionals did it. Hafner's group at Berkeley did a beautiful set of measurements where they trapped an ion, and they, with the help of another qubit, were able to plop it into a 0 and 1 state with different weightings, and they looked for relative phases that depended on those different weightings. And we had lots of nice ways of canceling out systematics in this case, and they found no effect. And they were able to put a bound on this epsilon parameter, roughly 10 to the minus 11.
What was it? Oh, this was for the AMU January case.
Yes, this is the photon case. This is all the photon case. The other option is to create a macroscopic superposition. As we saw, in principle, you do a measurement. The measurement leads to some macroscopic decision, and now you have a wave function which is a macroscopic superposition. And a macroscopic state is actually nice and coherent. Let's say a laser is a nice and coherent thing, or a big block of charge is something nice and coherent.
Is anything coherent? I mean, like a plane wave, all the expectation values are going to be 0, right?
No, the expectation value of a nu is non-zero for a plane wave. If you're in a definite particle number state, of course, it's 0, or in a thermal state, it's extremely tiny. But in fact, a coherent state is the opposite.
Oh, literal coherence. Oh,
Yeah, literal coherent. Yeah, yeah.
I meant to. I mean, okay.
Yeah.
I meant a plane wave. It's 0 in a plane wave, but you want it in.
This is a coherent state.
Oh.
It's a coherent state, yeah. So yeah, so then the idea would be to do some quantum decision measurement and then create some macroscopic superposition of something coherent, which would be, say, a laser or a voltage, an electric field, something that could be measured in the other world. And Alex Sushkov's group also did this last year. And this makes it look very fancy, but when you describe it, it sounds crazy, which is that they had random bits coming into a control computer that nobody was allowed to look at. Some of those bits were from a classical random bit generator. Some we took from IBM. You just buy some quantum bits from IBM and ask for them random. You don't look at them. And then, because maybe we don't 100% trust IBM, we also, Alex had a quantum bit generator in his lab, not at the same fidelity that IBM claims, but all of these bits were put into a data file measured, put into a data file, scrambled in a black box. And then when the bit says 0 or 1, a decision is made as to whether a voltage is turned on and off, and the voltage is measured for each period. And so the question is, when the quantum bit says off, does the other world where the quantum bit said on turn on a voltage in such a way that we see through this epsilonic effect, a coherent voltage source? And that experiment gave us about roughly a little worse than 10 to the minus 11 also. Now, the problem with, there are a lot of problems talking about nonlinear quantum mechanics, but one of the problems with experimenting on nonlinear quantum mechanics is the delicacy of it, which is that you have to be very careful when you are looking for nonlinear quantum mechanics. So let's say I give this talk, somebody hears about it, super excited, goes to the basement at Princeton something and does this laser measurement, and lo and behold, sees nonlinear quantum mechanics. The laser heated up the thing way over there, couldn't have possibly had to be nonlinear quantum mechanics. Great. So now the experimentalist wants to repeat the experiment. And the problem was that the left side of the experiment was fine, but on the right side, she had a little cup of coffee there and something overheated, spilled coffee all over the electronics. And so the person on this part of the wave function decided to repeat the experiment on October 2nd, but the one who measured spin down had to clean things up and fix electronics, and she ran the experiment on October 12th, 10 days later. And so if that was the state to begin with, rerunning the experiment on October 2nd after O up runs the experiment, this is the new wave function. This is the old result, and here is the new splitting, but notice the other version of the experimentalist did not do the experiment, did not turn on a laser. There was nothing here, nothing coherent to see. So what happens? This was the state of the experiment on October 2nd, but this was, or will be, and then this is the state of the experiment today after the first run. And so what you see when you calculate these expectation values, some glitch here, when you calculate these expectation values and you compare today versus the experiment on October 2nd, where only half of the wave function, the full normalized, norm-preserved wave function has a laser turned on, you get half the effect. And so the effect starts to disappear. You've polluted yourself quantum mechanically. And as you pollute yourself, split the wave functions, do macroscopically different things, you dilute the effect. Your colleagues think you're crazy, you can't reproduce it. It's a sociological problem with nonlinear quantum mechanics. It's fine if they do have different lives on either side, as long as they turn the laser on at the same time in both worlds. That is required. So without adequate care, superpositions may diverge wildly, and that prevents exploitability eventually. This is not automatic, but you need careful protocols. But then you worry that particles have been scattering for 13 billion years. Have the wave function been splitting up for the entire age of the universe? Haven't we already diluted the hell out of these things already? And that's, Bolchinski had a couple lines about that and then moved on, wrote D-Brains and had his life. Do you have a question?
Oh yeah, just trying to get a feel. So it is the case that this is a workable Everett phone, like they could effectively communicate between these branches.
So an Everett phone is causal, and yes, this would be a workable Everett phone. Yeah.
It's a causal Everett phone.
The Everett phone is causal. In fact, if you go through Joe's paper, it is causal. It's just weird. That's what he decides. All right, let's talk about sensitivity. Are we doomed to see anything locally? You know, what part of the wave function is us and what part is not us? Because it's us that is listening to this talk, making decisions about measuring nonlinear quantum mechanics. And so if we decide to turn on a laser in our lab and they don't, well, then the effect, this effect, which was originally just the expectation value of the laser field, electromagnetic field, now is suppressed by alpha squared. which is the probability or the amplitude squared on our part of the wave function. And one way of just using the same nomenclature is to say that there is an epsilon in my lab I'm going after, but it's an effective epsilon. It's the fundamental epsilon times whatever alpha squared is. Alpha squared may be extremely tiny. We may be a very tiny part of the wave function. And if we're a very tiny part of the wave function, we have no influence over the rest of the wave function, and we've suppressed these effects. So local exploitability determined really by the initial conditions, the initial state of the universe. So we're really sensitive to not just nonlinear quantum mechanics, but the evolution of the universe. And you could look at this and say, well, there's something beautiful about it, which is quantum field theory, quantum mechanics could be very state dependent, but we're in an attractor solution and we didn't see it. Could it be that we are in a very classical world? Could it be that the initial conditions of the universe are in roughly a classical-like state? And are there natural quantum amplifiers that are diluting us all the time? So you could look at the sun, you could ask, for example, maybe it's a bad example, but you take the sun, you say, if every emission of a photon is a quantum emission, and we are making the center of mass of the sun uncertain over 10 billion years after it's released 10 to the 60 photons. So you can ask, what is the width of that wave function? And it's about 100 nanometers in the lifetime of the sun. Big, macroscopic, thermal, messy, classical-like environments don't necessarily give you broadening of the wave function. If you have a lot of particles involved, you get nice square root of n suppressions. So changing classical evolution of the system requires something, maybe even coherent. Maybe you need, if n atoms go this direction or that direction, then they do something interesting. It changes the macroscopic trajectory of a system. If n, even if n is not too large, hundreds or something like that, and what you're asking for is, say, an order 1 probability, then this number gets very small very fast. So it's not guaranteed that every run-of-the-mill event in the universe is quantum driven. It could be very classical driven. You can ask about the weather. You can ask about my brain. It requires hundreds of ions to get any single neuron to fire. So it's not obvious that quantum is very important in these processes, that these aren't very narrow, classically driven effects. It's possible, it's reasonable to think maybe that quantum amplifiers are hard and that a lot of the evolution of the universe was classical. Except for our stupid field, our stupid field. A few years ago, there was some 750 GeV resonance.
Sorry, before you go into
yes,
that,
go ahead.
could you say that we see some CMB background if
yes.
I want to talk about this?
Uh,
But it could have been each fluctuation that was, up could have been down. So we're running 10 to the
for the not for the CMB, but for inflation itself. Yes. So the CMB is a
yes. The fluctuations.
Inflation is-
but yes, the inflation absolutely.
Yeah.
Inflation is going to kill us.
Standard cosmological inflation will kill it.
Okay.
Yes, and I will talk about that.
Okay.
3 slides. But just maybe I don't believe in inflation, or somebody wants to debate whether inflation, standard inflation with the quantum fluctuations seeding the universe happened. We've already caused a mess because if things like this, where the LHC sees something, it's a 3 sigma anomaly. If that 3 sigma is really quantum statistical, then we live on some tail of the wave function where we saw an anomaly in our field. Wrote 350 papers about this. And it affected my life personally. I didn't write a paper, but I almost wrote a joke paper, but then we didn't do it. But that means our field is very sensitive to this sort of quantum dilution, and really messing with quantum mechanics and making decisions based on measurements that may be quantum fluctuations, that has become problematic. That means that epsilon, if it started order 1, could be quite small by now. What about evolutionary dilution? What if RNA was a quantum fluctuation that was exceedingly rare on our planet? And that's why life started, not because there's some complicated non-equilibrium, but just it happened somewhere in the wave function, and that's where life is. And there's an anthropic reason why we're trying to figure out why RNA started. So that would suggest that tiny bit of the wave function is life on Earth, and most of the wave function is no life. There's an Earth here, but most of it, there's no life on it. Or maybe quantum fluctuations are very important for evolution itself. And maybe there is life on Earth, but many different types of species because things evolve differently in different parts of the wave functions. This is a lot less coherent here, but then this would suggest if you were at SETI, maybe you'd point your things downward and look for electromagnetic signals here on Earth. Epsilon might be small, but the signal is very close, so maybe you see something.
Do you mean from nonlinear quantum mechanics from the other alien branch of the wave function?
Correct. Correct. Exactly. Aliens. I told you, I'm making my mom very happy.
To a dinner anymore.
What? This is entertaining. Are you not entertained? So yes, Juan's question, the clean and obvious question, which is that if you are a believer that the universe is homogeneous and isotropic and was seeded by quantum fluctuations of a single field, those are quantum fluctuations that could have fluctuated up or down. You could ask, why does the universe, which starts with a wave function, which is almost exactly homogeneous and isotropic, there is a rest frame, but other than that, very uniform and symmetric. How does a homogeneous wave function become our universe? It's because it's a linear combination of statistically similar universes. And the full wave function is still very homogeneous and isotropic. But what we see, what we're entangled with, is not. We see a bunch of stuff. And so in most of the universe, the space-time point where the Earth is located is in empty intergalactic space. All right. What then? What now? What do we do? Well, the story is that the probes of nonlinear quantum mechanics are deeply tied to something unchangeable, which are the initial conditions of the state. And so we can imagine three scenarios. One where really only human dilution messed us up or diluted our part of the wave function, whereas the Earth is there, maybe the rest of the universe wave function is some tiny effects, but the dilution comes from things that happened by humans. You can imagine that the dilution happened much earlier if there were quantum fluctuations that were very important to life on Earth, or if canonical inflation happened, then the delta should be here. Then the Earth is very tiny. The Earth being here is a very tiny part of the wave function. And the rest of the wave function is locally very homogeneous and isotropic. If you have a quantum diluted Earth, but a classically evolved universe, something you could imagine doing is going somewhere where there is an ancient source of magnetic field, for example, carving away that ancient source of magnetic field, put a shield inside there, and then stick something like a squid to measure a magnetic field that is no longer there in our part of the wave function, but it is there in the dominant part of the wave function where there are no humans living on the Earth. So then you can look for that extra magnetic field coming from another part of the wave function. Something we thought you could do is we thought you could look at the Earth's magnetic field and put a shield and then go inside and say, well, the shield is not there in the other parts, but the shield, of course, is killing the parts of the magnetic field that is leaked into our part of the wave function anyway. So it's hard to do it, but there are ways to test. And really what you're looking for is some coherent source which is dominant in the other parts of the wave function. If such a thing works in the case of the gravitational field or the gravitational metric, you can imagine then that the metric itself has a wave functional associated with it. And where we may look at a star or a black hole or something in which we see orbits, matter would couple to our gravitational field and maybe the expectation value of the gravitational field, which is dominated by flat space. And in fact, that linear combination is non-trivially different than the Schwarzschild metric. And so it turns out at second order and post-Newtonian parameters, you would get some little effect, which does not follow standard gravity due to something that looks like a F or W or Minkowski background. The interfering metrics should also impact cosmological evolution today. Also, this is work in progress. But the bottom line is that if you want to see effects from nonlinear quantum mechanics, once we've been very diluted, look for fields which are turned on coherently in other parts of the wave function, different values than they would be in our part of the wave function. So future directions, we would like to understand gravity in terms of linear combinations of metrics. If that is a doable prospect and we feel hopeful about it, then you can ask about what happens at the black hole horizon if you have interfering metrics. The horizon is a very sensitive place to messing with quantum mechanics. Setting up a nice state that doesn't go haywire at the horizon, once you've done something to the way fields coupled to gravity, you could get violence at that horizon. So that's primary reason we're interested in the gravitational case. We're also interested just in how does nonlinear quantum mechanics affect inflation. Inflation itself could be driven by some of these effects. And we have some preliminary work, but we haven't gone too far. And then you could just simply ask about model building with fields that are turned on, like the curvature or the Higgs field or something like that. Can those be used to solve the hierarchy problem, cosmological constant problem, things like that? Standard model building games. So my first statement is just that there are consistent ways to explore deviations from quantum mechanics. It actually is quite simple and clean. And locality, which is natural coming out of a local field theory, means a lot of the past tests are no longer relevant. And so that's why we're approaching with new probes for local effects. Nonlinear effects can be experimentally tested by amplifying quantum measurements, creating macroscopic superpositions, but we worry about pollution. We worry about the fact that quantum amplification actually suppresses local nonlinear effects. And we're thinking about how non-zero fields, those expectation values in sort of typical states of the wave function may still be something that's detectable. Now, of course, if nonlinear quantum mechanics is locally accessible, we will dramatically change what we can do technologically, but that we'll talk about if it's actually discovered. So I'll stop there.
Yeah. Can you clarify if I do experiment A to open up an Everett fountain?
Yeah.
And then I do an identical but unrelated experiment B to open up a second Everett fountain.
Yeah.
Does that degrade the first one? Is it now worse?
It does. Every quantum amplification you do will cause a degradation unless you've lined up sort of what the outcome of macroscopic evolution is. So let's say I have a laboratory, it does robotically its own experiment, sees nonlinear quantum mechanics. I just get a result out that it saw nonlinear quantum mechanics. I'll see that in all parts of the wave function. And now if I decide to do another experiment to show my friends, there's no dilution. What matters is if these branches start to peer away from each other.
I see, if they do different things.
That's right.
Okay, got it.
That's right. So the expectation values of some coherent field, like an electric field or a potential or a laser or something like that.
Yeah.
So if the laser is turned on in every world, then you get the full coherent effect. But if the world start doing different things and talking about different things.
Got it. Yeah, that makes sense. Okay, thanks.
Sure. We started panicking, like, because the bounds of time we were looking at it were so weak. We thought, if it's true, could you break 256 encryption code? Because you can do a bunch of spin measurements and parallelize your laptop or a Cray computer, and then you could get this incredible N factor to do things very fast. And we realized that you can't do 256-bit encryption with the strongest Cray computer in the life from the universe. You can do 128 in about a week, but you couldn't do 256, and the US was protected by 256, so we don't care. So we put the paper out. The bounds are much better, so I think 128 is becoming harder.
So you could also say that there is nonlinear quantum mechanics and inflation erases it.
Yeah, no, it's
also interesting.
a bizarre attractor solution to
And
this.
it erases it by e to the minus the volume of our universe, roughly, I guess.
Uh,
Whereas cosmic variance limits on even in principle whether we could detect it or not, or just one of a square root. So it's like literally impossible.
It's completely erased. It's completely.
I mean, even
What-
in principle erased.
Yeah, what do you care about? You care about the size of my local experiment and the variation of where the Earth with us on it would be.
I'm just saying.
So I don't even know what that coefficient is.
It's amusing that nonlinear quantum mechanics kills itself exponentially, whereas linear quantum mechanics gives itself a square room for error. So that you can never even tell the difference, even in principle, even if you want it.
Yes, I think so. Unless, like I said, unless they're coherent.
Right. No,
sources,
I meant
but yeah.
something like.
Yeah, local, you will never be able to tell. That's right.
But you can sort of consistently imagine, all the tests that you're talking about are just consistently, at least locally imagining that
Give up on inflation. Maybe it's not.
but is it
true.
just give up on inflation? I mean, are we not, I guess,
Inflation is this whack job killer exponential crazy number. The other dilutions, we don't know. And so I don't know how to put a number on those things. So at this point, we're just asking how well can we measure it?
but I don't know. I mean, random radioactive decays, given, that's part of your quantum.
Yeah. The point is that they create a coherent macroscopic superposition. Yeah.
I guess I would think they do. I mean, even you don't need to create aliens, but anyway, okay, I understand that. That's the.
But it's not one particle decaying, it's.
Yeah, no, I understand.
Yes, if I do a Schrodinger cat measurement with a single nucleus, then yes, I've done it, but I've forced that. But typically, we're talking about large numbers and incredibly tiny widths.
Any other questions for David? All right, if not, let's thank him for a really stimulating talk. Thank you.